We have been looking at propositional logic, and this is probably the last class that we will look at this, and in particular we were looking at indirect proof methods. So, we saw this system called Tableau method. So, just to do a very quick recap, let me take a small example. So, supposing we want to show a particular formula to be true. So, let us say that this is the formula that we are interested in, and it says that P or Q implies P and Q. So, let us say for argument's sake that we want to show that this formula is true or valid or under all valuations essentially. So, the method says that what you do is you take its negation. Both the indirect proof methods that we are going to look at take the negation of the given formula, and then we try to show something. In the case of a Tableau method, we try to find a satisfying valuation for the negation of the formula essentially. And if we cannot find a satisfying valuation, then we conclude that the formula cannot be negated essentially. So, let us just quickly look at this method. So, we apply the rules that we had for the different connectives. So, to make this formula false, we have to make the left hand side true and the right hand side false. So, we just, as is our custom, we will put a tick mark when we have dealt with this. Now, we have two formulas, both of them are going to introduce branching. So, we do not really have too much of a choice here. So, let us take the first one, we introduce P or Q. So, we have dealt with the second formula, then we do the third formula. This says that not P or not Q. Now, the way to break down the third formula, we have to do it in each of the two branches. This is probably the first time we are looking at it. So, it serves as a reminder that we have to do that as well. At this point, we notice that this is closed because there is a contradiction along that path. We also see that this last leaf is closed because there is a contradiction along this path, but the other two paths do not have a contradiction. Further, we cannot do anything any more breaking down because everything is already at an atomic level. So, we cannot refine this tree any further essentially. So, this means that we are able to find satisfying valuations essentially. So, there are in fact two valuations, one is given by this branch. This says that if P is true and if not Q is true, which means or Q and Q is false, then we can make the original formula false essentially. We can make its negation true and therefore, we can make the original formula false. Likewise, in this valuation, if we have not P and if we have Q, then we can make it false. So, we are left with a derivation which is, as we say, not closed. So, what we need in a Tableau method is given a formula sentence S, we need some kind of a breakup of the formula, where every branch is to be closed. Now, if every branch is closed, then we say that the Tableau is closed. and if we started with negation of S, then this means that negation of S is unsatisfiable, which means that S is valid or S is a tautology. So, a proof in the Tableau method is derived by producing a tableau where every branch that we can see is closed essentially. And we would say that a Tableau method is complete what is our definition of complete? That for every valid formula we are able to produce a closed tableau. Well, I have written valid formula here, but you must keep in mind that when we have to negate it before we start constructing the tableau. So, I should maybe write unsatisfiable formula. Now, what are the choices that an algorithm will need to make here? Basically, the choices are as to which of the constituent compound sentences we need to break up essentially. And we have mentioned in the last class that if you break up those sentences which do not include branches, then you will have to probably end up doing less work. But there is also another choice which we do not often talk about, which is that sometimes you can close a branch quickly without going through many breaking ups essentially. If you could do that somehow, then if it is a large formula especially, then you could actually have a shorter tableau which is closed essentially. But an important feature is that the tableau must be closed, which means every branch must be closed essentially. So, you can imagine that the proof can sometimes be quite long essentially. So, today I want to look at a different method which is called the resolution refutation method. So, as I mentioned towards the end of the last class, this was invented by Robinson in around 1965 or so, and since then it has proven to be a very popular method essentially. So, like the Tableau method, this is also a refutation method in the sense that it works with unsatisfiable formulas. And it shows in this case that you can derive a contradiction. If you start with an unsatisfiable formula, then you can derive a contradiction essentially, which means you can refute the fact that formula is true essentially. Why is a contradiction bad for a logic system essentially? The reason for that is, as logicians say, that if you have if your knowledge base is inconsistent, or if you can derive a contradiction from a knowledge base, then in fact you can derive anything essentially. So, let us just do that a small example to show this. Can derive anything from a contradiction. So, let us take a simple contradiction which is just a sentence which says P and not P. which obviously is a contradiction, because you cannot make both p and not p true at the same time. Then you can, by using simplification, infer p. You can also infer not p. You can also infer not p or q, which is addition, the rule of addition, which says that you can always use the disjunction to add something else, and from this, as you can see, you can infer q. This is from 2 and 4 and disjunctive syllogism. So, I will just write d s here. So, you started with p and not p, and you could produce q. Now, obviously, you can see that there is no connection with of q with p and not p, and you can practically derive anything from a contradiction, which is the reason why when we look for knowledge bases and logic systems, we are interested in three properties essentially. One is the property of soundness, which if you remember says that if a knowledge base derives a formula alpha, then that formula should be entailed. Then we have completeness, which says that if a formula is entailed, then you should be able to derive it. And the third is consistency, which actually is connected to soundness, but we often state it separately, that cannot derive both a formula alpha and its negation essentially, because then you have a consistent inconsistent knowledge base, and then you can virtually do anything essentially. Okay. So, the resolution method starts with an unsatisfiable formula, and then it shows that you can derive a contradiction. We will look at that shortly, how it does that. But before we do that, one comment, that the formulas that it can look at are in conjunctive normal form. Which when we move to higher order logics, we will also call as clause form. So, I will begin by defining what is conjunctive normal form, and then we will look at the method itself essentially. Or CNF, which is the short form for conjunctive normal form essentially. So, a formula is in clause form if it is of the form where it is a set of clauses and C 2 and C 3 C n. A set of clauses. Okay. So, I am using the term a set of clauses, but obviously, the formula that I have written is not in a set notation, it is in a logical notation that we have in the logic language that we have. So, when we write a set of clauses, we may sometimes just denote it as C 1 comma C 2 comma C 3 comma C n. So, we often write clause form formulas as a set as well essentially, where each clause C I can be written as d 1 or d 2 or d r. And each d I is an atomic formula or a negation of an atomic formula. So, we call this a literal. So, each d I is a positive literal or a negative literal, and by literal we mean an atomic formula. And like we do for clauses, we may also use a set notation for the each clause. So, we can write it as d 1 comma d 2 comma and so on up to d r. So, what can we observe about this? That the only connectives that we use are negation and or, and in addition the negation is applied at the innermost level in some sense, and then in the next outer layer or is applied, and then in the outermost layer and is applied. So, for example, we may have a formula like this P or Q and not P or R or S and S or T or not Q. Such a formula is in disjunctive, so conjunctive normal form. So, this is C 1, this is C 2 and this is C 3, and this is a conjunct of 3 clauses essentially. So, unlike in our earlier notation, here these are literals essentially, they are not propositional variables anymore, they are the literals, which means they are atomic propositions or negations of atomic propositions. Now, we can convert any formula to clause form. We will not do this now, but maybe when we look at first order logic, where we will also be interested, we may look at the procedure. But the basic idea is to replace every other connective with either one of these 3 connectives or combination of these 3 connectives, and then apply De Morgan's laws and distributive laws and associative laws to basically arrive at this particular structure that we are interested in, where at the outermost level we have clauses, then inside each clause there is a disjunction of literals essentially. Now, this comes with a warning. May blow up essentially. That a formula, when you convert into CNF form, it could possibly blow up into length essentially. So, as an example, if you were to try to simply expand a formula like P is equivalent to Q, you will see that it will have 3 or 4 connectives which will come into place. Okay. So, now we assume that we have a formula in CNF form, and the resolution method is based on this following. On a tautological equivalence, which is the following, that if you are given a formula which is of this kind, then this formula is equivalent, logically equivalent to the same formula repeated, which of course is trivial, but also a new formula which is added, which is a new clause is added, which is Q or S. So, if you accept this as a tautology, then you can accept the resolution method as a sound method. And I will leave this as a small exercise for you to show that this is a tautology. You can use in fact any method to do that, but this is just an instance of the kind of formula that we are looking at. If I use a more generalized notation, then what I really want to say is that, let me first state the resolution rule. And the resolution says that if we have these two formulas or these two clauses given to us, the first clause is P or Q, the second clause is not P or S, then we can add the clause which is Q or S to the set of clauses that we have essentially, which is our knowledge base essentially. And essentially you can see the connection between this and the tautological equivalence essentially. But the generalized form of resolution rule is as follows, that if you have a clause of the kind P union some sentence 1, remember that we can use a set notation where every clause can be seen as a set of elements which are connected by an or. So, this is something similar to that, except that here S 1 is a set which may have any number of literals inside that. So, it is not that we can work only with clauses which have 2 literals, it can be any number of literals. The only thing that should be there is that one of the clauses should have a literal P and the other clause must have a literal negation of P. So, there this sign is the union sign S 2, and from this we can add S 1 union S 2. So, what I have written on the left hand side is simply an instance of what is there on the right hand side. In general, the clauses can be of any length essentially. So, the refutation part. Supposing we start with a set of clauses C 1, C 2, C 3, C n, and we apply the resolution rule to some 2 clauses from this, which means that we take some C I and C j and we will get some new clause, let us call it R 1. Then the tautological equivalence that we wrote says that this is equivalent to C 1, C 2, C 3, C n, and so let me use a different color here R 1. We have, so where R 1 is obtained by some C I and some C j deriving R essentially, or in the notation that we have been using C I, C j and R 1. So, based on the tautological equivalence that we mentioned, these 2 formulas are equivalent. Remember, these 2 are formulas written in clause form, a set of clauses. Then we can derive one more clause C 1, C 2, C 3 C n R 1 R 2, and in this fashion we can go on deriving clauses. And we will terminate when one of the clause the empty clause is derived. So, let me denote it by actually adding the empty clause. So, the empty clause is represented by a bottom symbol, and the empty clause is can be derived whenever we have p and not p, and then we can derive the empty clause. So, we use either the square box or the bottom symbol to denote the empty clause essentially. So, if at some point we end up deriving the empty clause, then we can terminate essentially. So, which I have written here as the bottom symbol here. So, what is the logical argument that we are making here? We are saying that these different instances of knowledge bases or formulas or set of clauses are logically equivalent, because we have shown that adding that extra resolvent. So, this is called the resolvent. The two sides are logically equivalent. So, the first set of clauses, which is C 1 to C n, is logically equivalent to C 1 to C n plus R 1, which is logically equivalent to C 1 to C n plus R 1 plus R 2, and so on and so forth till the last one we have derived. Now, what is the truth value of the last clause? The last clause is of a conjunct of the kind C 1 and C 2 and C 3 and R 1 and the bottom. Remember that the bottom part always evaluates to false. So, any formula which is false and the conjunction of anything else will be false essentially. So, the last clause is false, which means that this must be false. When we say false, we mean unsatisfiable. So, let us quickly try and end with a small example. Let us work with one of our favorite sentences right now, which is the second axiom from Frege, which said that P implies Q implies R, the whole thing implies P implies R implies P implies Q implies P implies R. So, if you want to now use a resolution method, we must negate this entire formula and then apply the resolution method essentially. So, let us negate this and we want to put it in clause form. So, the left hand side, so when I push the negation inside, I will get this P implies Q implies R. Okay, first I must convert it into clause form. P implies Q implies P implies R, which I could have actually written as not of this or this. So, now when I push the knot inside, this will become this knot and this knot will cancel. So, I will get P implies Q implies R, and so I am working towards it being in a closed form. P implies Q and knot of I am pushing it 2 steps here, P implies R essentially. So, when I write this as not P, or I am skipping a step here, or R. So, that is one clause that we have. This clause would be not P or Q, and this will give us 2 clauses, one is P and the other is not R. So, we will end up with 4 clauses. So, let us draw a tree like structure, which is actually called a directed acyclic graph in the case of resolution proofs, and we apply the resolution rule now repeatedly. So, that is a basic algorithm, you apply the resolution rule repeatedly. So, let us say we apply between this and this. So, we have P here and we have not P or Q here. So, we can throw away that and you will be left with Q here, and ignoring the fact that we have a formula with 3 literals. So, I can ignore that bracket here, I can apply the resolution rule again. So, I will throw away Q and not Q and I will be left with the remaining, which is not P or R. Then I can use this again, P and not P I have. So, I throw away P and not P and I will get R, and now you can see that from this and this I derive the empty clause, or I could have written a empty box, which is actually the traditional way of doing things. So, let us do that. So, this is called a resolution DAG, or resolution refutation or proof essentially. So, DAG stands for directed acyclic graph essentially. So, this actually gives us an example of the resolution method. I have sort of done this a little hurriedly. We will come back to the resolution method when we move on to first order logic, because I want to now move on to a more expressive language, which is first order logic, and we will do that starting in the next class onwards essentially.